with you outside of class time. I'll let you look at that on your own, related to the Schmertman method, which was kind of the intended content for today. And I'm able just to give that to you as an asynchronous activity of check out that video. It's a rather short video, 26 minutes, I think. So I envision it being quite dense, though, where you'll be wanting to pause it on occasion and make sure you get all the notes and so on. But it goes through that content thoroughly. I would also like to identify that another video has been posted of consolidation coverage, and that relates to magnitude of consolidation. For those that had me, this is in 381. This is a video that I've used in 381 in the last, since COVID, let's say. In that case, if you had me for the class, you've seen that content and you wouldn't need to see it. If you feel comfortable with magnitude of settlement type calculations, there's not a need. I'm not forcing you to view that, but I will. It is posted on Canvas and available for you for a tune-up on that material. And I think it's, relatively quick coverage of that, and that relates to how much settlement will be occurring. We will follow with that on how long that settlement takes to occur next time rate of consolidation. And that is a fairly hardy conceptual topic in soil mechanics, about as hardy as it gets, I would say. And it's a nice synthesis of geomechanics, the compressibility of soil, along with flow of water in soil, all coming together in a single analysis of how long does this consolidation take. So for today, we will revert back to stress distribution for one analysis that I neglected to cover. I mentioned it in passing and said, I'm printing something, I'll get back to this. And I never did get back to it. So I want to make sure that I hit that. And that's the, oh boy, sorry about that, Newmark influence chart. And it's a nice method. It's a little bit onerous. You'll see how that goes, but it can be highly convenient for certain cases. And then I'd like to preview homework 5. Just take a look at it with the group and give you a little bit of a heads up of what's coming your way in that, as it is a rather involved problem in one case. And then I also want to go through a thorough introduction to the design project. So these are both items that are fairly well off on the horizon in terms of due dates. I set the due date for homework 5 already as November 13. That's a Friday. So it's 2 weeks out, and there's plenty of time. However, we have some big things coming into the pipeline here with the design project kind of as a background activity and so on. By the way, this homework 5 is the last homework of the term. So you'll be seeing this as a homework assignment. Homework 4, which is coming around and due on I set the deadline for Tuesday, the 4th of November, I believe. And I'll check that when we get around to Canvas. But I am somewhat flexible on that, meaning I could allow extensions case by case basis and so on. And I may just kick it out one day further to avoid any kind of conflict with the election. I do not want that being a concern when voting is absolutely important. And I want to give you all the opportunity you need to make that happen. So I saw SLO County, by the way, has the highest voter registration ever. So good stuff. And I don't know if congratulations to you is in order, but I'm sure that's due to a bunch of young folks coming together on this, and first time voters and so on. And that's a good thing these days, I think. We need to be heard. So I'd like to move on to the Newmark stress diagram, stress distribution uh, diagram. I'll show you that diagram first and then have a page related to instruction on how you use it. This is what it looks like. It's in the handout associated with stress distribution. So I'll casually call this a spider web, and I hope you see where that term is coming from. And this has something called an influence value written on the chart. All of these have such an influence value. If there is a chart produced for Newmark, it contains that number on it, and it contains a line associated with a length typically called AB. And these come in a variety of shapes and sizes. I've seen them with some real hatched out, highly detailed quadrants on occasion. You'll see this in, for instance, the PE review manuals. I know Lindbergh, as an author, a great review manual, by the way. If you are prepping for any of those licensure exams, that's a good author to keep in mind. He has, I think it'd be a few of these, and in other resources, I've seen several. So it's not just one, but they all look kind of like this, is what it amounts to. And on that Newmark chart, if we look at stress distribution using that chart and that method, we need to first establish a scale for a plan view depiction of the foundation drawn, or the loaded area, I should probably say. More accurately, this would be called loaded area. And generally, that is a foundation, and that's why I wrote that. I was just thinking as I was writing, and that's the normal thing that you're solving these for. And that scale is going to be AB is equal to the depth to the point of interest, the depth below the loaded area. In other words, usually depth below the ground surface, or depth below base of foundation if it's embedded, which a foundation usually would be. But these are set up, elastic theory, semi-infinite half space, all that business again. So it's typically depth below ground surface in that highly idealized scenario. And the AB is this distance here, and the idea is that distance will equal the depth to your point of interest. If you're 12 feet below the foundation, or if you're 20 feet below or 3 feet below, your foundation then would be drawn to different sizes on the graphic. You then, once the scale is established using that, you then draw the foundation, or again, loaded area, on the Newmark chart directly, and you draw that to scale. And you have your point of interest, that point which you're trying to determine delta sigma for. In the past, Boussinesq chart, we've used corner of foundation, for instance, center of foundation, that kind of thing is what I'm speaking of here. And that point of interest should be located at the origin of the circles, or the centroid of the Newmark chart. So your point of interest looking down on your foundation should be that center point. And then when your foundation is drawn to scale and with the location of interest properly identified as the centroid of that chart, and appropriately scaled, and so on, distance from there, or whatever it is, you will count the number of elements contained within the footprint of the foundation, and we call that number M, little m. And after that, we calculate the delta sigma. And it is a simple calculation here. It is M times this influence value, which is provided right on the chart. All these charts have a number provided for you, and it's just a constant that applies. So I'd like to show you how that unfolds on this chart. So I would like to look at a scenario where we are trying to calculate the delta sigma beneath the corner of an 8-foot by 8-foot foundation at some depth below the foundation, base of foundation of 12 feet. And what that means is that we need to grab our Newmark chart and establish what the scale is. And that scale will be established using this distance. So AB, call it 1 inch or whatever that is on your scale. And the nice thing about these always being embedded on there, you can photocopy it, enlarge it, or you can put it on a PowerPoint screen, and it can be huge, and it's all valid because of that. So with this problem, this is now 12 feet for this example, only for this example, because I'm at Z of 12 feet. So this is Z, and maybe Z is a better term for that distance, as that is generic, and it's only 12 feet for this example. So with that being 12, we want to have 8 by 8 established. And I'm just going to eyeball this. I mean, you certainly, if you're doing this, you might use a ruler and dial it in a little better than this, but I'm going to go with 2/3 of that distance. So something like that, and bring that up here and show our foundation in the right location at the right size. And by right location, I mean we're interested in corner of foundation, stress under the corner of the foundation, 12 feet down. So the 12 feet is giving us our scale, and the corner is making it situated that the corner of the foundation, the point of interest, is indeed at the centroid of this chart. So that's the first main hurdle of this methodology. And we've drawn the foundation now. Next up, we have to count the number of elements contained within this. And this truly is a pretty simple thing. You just count it out. And I have found for myself that using 0.1 for a precision works quite well, because just it's easy to keep adding to it and so on. I'd say from a precision standpoint, it's probably closer to about 1/4 of an element that you have capacity to track this. But then you get into too many decimal places floating around and so on. And I find it just a little bit easier with the other. But what I'd like to do now is count this. We'd have 1 full element, 2 full elements, maybe 2.5, 2.5. 3.5, 4.5, 5.25, 5.3, let's say, at that point, 6.3, 7.3, 8.3. I'm going to call this 9.3, including both of those, where that little corner makes up for this little corner getting chopped off. So 10.3, 11.3, 12.3, 13, 14, 15, 16.2, let's say. And I'm going with a approximately equals. M is about 16.2 on this one. Are there questions on drawing this out or coming up with that value, 16.2? Any concerns? Okay. At this stage, we are ready for that last step of the calculation, which is delta sigma is M times IV. So delta sigma is 16.2 times 0.005. That is the published value on that chart. Okay. And I knew that without looking because it's a fairly common number for these Newmark charts. Most of them have that number. And what do we have for a number then on that? And then that would also be times, I'm sorry, I missed a parameter here. You need to have a Q naught on this thing. So I'm going to go back to the instruction sheet times Q naught. That blue pen again. And that's the stress on the loaded area. And I realized we're running into a problem here of not having the correct units. So dimensional analysis often helps you out with this stuff and make sure you're doing a problem correctly. So there's a lesson for you. Always check units and keep track of them on the fly because it can let you know of a hiccup going on, which I had in this problem. I had missed that in the equation. So just a fair note on modifying that last line of this page of instruction to include a Q naught term. M times IV times Q naught. And I will add a Q naught to our problem statement just so we do have something we can solve. Just put it in parentheses here, Q naught 3000 PSF, let's say. All right, so delta sigma would be 16.2 times 0.005 times 3000 PSF. And do we have any calculators revved up here to get a number?
243 pounds per square foot.
I didn't hear that. I think that was Evan.
243.
243. And PSF, I heard, and that would be correct. Your units hold, and these are dimensionless. So what would happen in this analysis if you were at a shallower depth? What would happen if you were looking for this same delta sigma, but at a 6-foot depth instead of a 12-foot depth? Is that going to be higher or lower?
Higher.
Lower.
I'm hearing both. I need a justification from maybe both.
At a shallower depth, the scale will be larger, and so your scaled foundation on the chart will be larger, and your overall delta sigma will also be larger as a result.
That sounds pretty solid. I did not see who had the comment that it would be lower, but if you care to chime in with a counterpoint, we can entertain that. Okay.
I looked at it wrong. It's definitely higher.
All right, it would, and Evan gave a very eloquent description of it, so I don't even think I need to repeat that. It, in short, ends up being a larger diagram over here due to the different scale. And then you'd have more elements inside it, a higher M, and therefore you do have a higher delta sigma. And hey, what do you know? That's gut feel intuition telling you that also, that you would expect closer to the foundation to be higher stress. So that is the general routine on this problem. What if you have a huge foundation? Just, let's say you got a complex, the Department of Defense is putting something together and they're building a structure that's a half mile by a half mile. And you're looking at a point 12 feet below the surface. Or even for that matter, 50 feet below the surface. What's going to happen to the math here on this? What would the building look like on this graphic if you drew that up? What if you had just an enormous building?
You just need a bigger chart or to make A and B small?
There's not a need for a bigger chart. This actually handles it. Out at the edge, it's still valid. And if it goes beyond the edge of the chart, you're fine. You just call that a full element and you're done. That's, getting far enough out that you just say, hey, it's a full effect at that point. So what would that building look like on this graphic? If we started coming around and counting cells or elements on that, what would we be counting?
It'd just be that entire corner of the chart, right?
It would be the entire corner of the chart if we were doing under the corner. If we were trying under the center, it would be the whole chart. Okay. And if you are, pass through here and count every element on here, how many elements are you going to find?
200.
200. Where'd you get that, Evan? You're quick on the uptake there, unless you count real fast.
I counted them.
You did. All righty.
It's also 1 over 200 is 0.005.
That's it. This number has a meaning. It's 1 over number of total elements on the chart. So if you have a huge area, you're going to count the whole number of charts, the whole number of elements on the chart, I should say. And then you will have 200 here times 1 over 200 times Q naught. In other words, that load at the surface is acting like a new soil layer, which really is what it is. At that point, it's a one-dimensional problem. There is not distribution of that load at that scale, at least. So I hope that provides a little bit of context on, I'll call it the meaning of that chart, given that this is frankly a pain in the neck to do. And you can revert over to the Boussinesq M&N table or a more simple tabulation of answers in this regard. This would not generally be a go-to method for a simple geometry like this. However, if you had a historic fountain at that location and you're interested in establishing how much is that going to settle, that could be a highly relevant sort of problem if you're building an addition to an old schoolyard or something, or an old abbey, something that has a very weird geometry, kind of a courtyard type building. Something like this, and that's not even the building yet, that's just the courtyard, but yeah, I think you're getting some of the point here. you might have a building that looks something like this. See this shaded area here. Now, if you tried to hammer out delta sigma using the M&N chart on a building that had some crazy shape, something like this, which again would be a relevant challenge. I mean, there might be problems that have this sort of concern, and you're interested in what's going on right there at the center. You'd be at the M&N chart all afternoon. And here you can grab Newmark influence, patch it out to scale, count your elements, you're good to go. You're in and out in 10 minutes. So it is a matter of perspective on what is being loaded and the shape of that and so on, and the resolution needed and that kind of thing. It's a neat method though. It's kind of cool and that it's graphical and so on. It absolutely is, you know, valid and comparable to the other, you know, Boussinesq, Westergaard and so on. And I will have you using this for homework number 4. There's one problem in which you're going through and using multiple methods to get a delta sigma. And I would like for you to actually show it like this, meaning hand in a copy of this with your work shown above it. Okay, superimposed over it, I mean. All right, and it's a simple one, so you won't, it'll just give you a sense for how does that answer compare to the other methods. I'm not having you get into some crazy thing like this, weird shape. Questions on Newmark? Okay. All right. Let's move on to homework number 5. I'd like to give you just a quick preview on that. And we'll probably do another preview in time after you've had the content related to time rate of settlement of consolidation, by the way. So, one sec here. Okay. Homework 5 looks like this. This is live on Canvas, so you've seen or you have access to this. And this is a situation in which they're building a museum in Chicago, Illinois, and want to establish the potential stretching of a fiber optic cable that is running just next to a foundation. It's at a depth 4 feet below the foundation. You'll see elevations provided over here. And there is a line of symmetry going on. So this is a square foundation, B/2 shown like that. And if we look at a plan view, it looks something like this. And it's important to recognize that the cable is running right under the edge of the foundation. And while the problem is symmetrical, meaning you'll actually you're going to be making some plots of what's going on with delta sigma, what's going on with consolidation settlement and so on. And while the problem is symmetrical, you do need to consider the entire foundation. And that's a really important component of this problem. You need to have the 6x6 foundation implied in your calculations. And what's going to happen here is you are going to assess what is happening here, here, 10 feet over, and here, 10 further feet over. And given in the problem statement, 10 further feet, which would be off the page here to the left, is known that there's no settlement occurring there. And you can use that in your analysis. And what's being requested of you is to use the Boussinesq M&N chart, or develop this into a spreadsheet program. And that would be utilizing the equations that I shared with you from the Salgado textbook, the MN C1, C2 business. There's a fair amount of parameterization there, but it's not certainly simple stuff. It's all just fractions and this kind of thing. I would say that you would be wise to consider doing a spreadsheet for reason of efficiency in terms of entering this chart multiple times and so on. And more important than that, it will help you with the design project still coming. So you're going to be needing the spreadsheet programmed for that exercise, so you could get it done here ahead of time and check the box. I would say that it would be appropriate for you to be proficient using the Boussinesq M&N chart, the actual chart solution, because that may come up, for example, final exam, where you would not have access to spreadsheet. And I'd be fine with you utilizing an equation, but that on a hand calculator is fairly involved stuff, and the M&N chart is pretty quick business. So in this case, you're going to use the Boussinesq chart or spreadsheet, but you're going to use this elastic theory stuff that we've been talking about for some days. And you're going to calculate the vertical stress profile for the midpoints of the compressible layers. And the 6 points of interest are shown in the sketch. I was looking down at them earlier, showing 3 points of interest. But if we look in cross-section, you actually see ABC. And below that, there is DEF going on at a different depth. So they are in the same vertical location. So B and E will actually talk to each other to some degree, and we'll get to that in just a bit. But it would be a separate calculation for stress distribution or delta sigma at this point and this point, because the depth below the foundation is actually different. I've given parameters here in terms of the clay. There's a gamma, there's a C sub C, there's a C sub S, there's a void ratio, a pre-consolidation stress, and a C sub V, a term that we'll be talking about with time rate of settlement. So this homework includes time rate of settlement. And so this is the overview looking down on the problem. And you are to establish the stress change with position for those 6 points. And I'd like for you to plot delta sigma versus lateral distance from the foundation for those two depths of interest. The depth according to A, B, and C, and a different plot for the depth of DEF, or at least a different curve on possibly the same plot. I'll leave that up to you. And intuition would say, boy, you certainly think that there's probably going to be a greater stress change right beneath the center of that foundation than far away, 20 feet away. And I'll let you explore how that unfolds with the actual numbers. And from the results of this, you're going to actually calculate the consolidation settlement profile, which would be settlement versus lateral distance from the foundation. And something to note here, I mentioned that these are talking to each other. The settlement at this location, right at the center of the foundation, under the center of the edge of the foundation, I think that's an accurate description of where that point is, will be a summation of the settlement of the top layer of soft clay and the settlement of the medium layer below that. Because you could picture this medium layer down here undergoing some settlement. I don't think it's, I guess I need to be around characters to have that stay as a shape there. I'm not even there anymore. In any event, this layer will be undergoing settlement, consolidation settlement, due to the delta sigma being applied, which you'll calculate. And that means that this layer will become shorter, thinner. It will compress. And what you have to recognize here is everything above that point is going along for the ride, including the foundation. So if this layer settles 1 inch, point C is moving down 1 inch just because it's going along for the ride. Separately from that, you'll also make a calculation of the settlement of this layer, the soft clay layer. And you might have 3 inches for this and, for instance, 1 inch here. And that would mean that the foundation will settle 4 inches because it's settling for both of those. It is identified here that this is incompressible sand, so we're not going to be getting into sand settlement in this problem at all. And we can assume the underlying gravel similarly is incompressible, as well as this little bitty sand seam here that's discussed in relation to the time rate portion of the problem. Questions on that so far? Okay. I think it's a reasonable assignment from standpoint of, you know, the tasks at hand here, but it does end up being a little bit of bookkeeping and a lot to manage because there's all the points and so on. So just a heads up, this would be one not to leave for an hour and a half before it's due and try to pull this out quickly, as it might take a little bit of reflection on your part and thinking about it. What we're going to do here next is assume that the cable is fixed 10 feet beyond the edge of the drawing, and that's that aspect where it's not settling at all. So it's just locked in there. So 30 feet from the center of the foundation, it is locked in there. And what you're to do with that information and with the information that it is settling along that profile that you've now graphed out in this portion of the problem is to assess the tensile strain of the cable. And this brings us back just to pure mechanics. And what I'm showing here, I'll share the screen, a different one. Is that strain is change in length over initial length, nothing new there. And that's just old, you know, fundamental engineering stuff. And I'm looking at that fiber optic cable from the center of the foundation, or the center of the edge, off to that point where it's locked in 30 feet away. So this is L0, 30 feet. That's the original positioning of that cable. And any gut feel on this one's not going to settle. We know that. That's given in the problem effectively. It's locked in. Any gut feel on where we're going to get the most settlement on this thing? If this is our foundation over here.
Right in the center.
Right here. Yep. So you're going to have a lot of settlement here because you have a lot of delta sigma. You're going to have less over here, less over here. And each time it's going to be a summation of the 2 points or 2 layers acting in concert. We would have a lot of settlement happening there, less happening here, even less happening here, and 0 there. So what we have now is a new shape for this thing. You can get as fancy as you like with this. I'm fine with piecewise linear interpolation, fancy language for connect the dots. That's fine for this exercise. If you want to get into a, smoothing curve fit mathematical function that it represents this, charge on. I'll invite that, but not require it as an expectation in the assignment. And this 30 feet would be L naught, original length. This here would be length final, and delta L would be length final minus length initial. Questions on that? So we're actually looking at a stretching of that cable. And you could imagine that would be pretty serious stuff. You get an urban location and a cable breaking, you're in for a world of trouble in terms of connectivity and so on. As you see, this would be a graph actually that I'd be looking for, this red line of the settlement profile. So that would be the answer to part, I think it was part B, something like that. And if you want to show the whole graphic, mirror image, that'd be fine. But this would be sufficient because we know that it's a mirror image. And next up will be the fact that the cable can actually adjust to some stretching if that stretching takes place slowly. So the main concern here is shortly after the load is applied. And the question now is compute the average tensile strain of the cable after the first 4 months of loading. And this will be head-on time rate of consolidation stuff. So we haven't covered this yet. We'll get to that next week. And then you'll be able to tackle this. It's a pretty straight or simple conversion from part C to part D. You'll find that to be quite reasonable once you understand those theories. But this brings us through points A through C and lets you dive into this thing if you care to. And again, it's not due for 2 weeks, so I'm not pushing it, but also making it available and letting you know we've got plenty going on in the pipeline now. Currently 3 things happening at once. The homework 4, homework 5, our last assignment again, and the design project, which will be in your hands in a moment here. Next up on this assignment is some consolidation, laboratory data, and interpretation of that. And one limitation of the quarter system is that the full suite of geotechnical tests do not get to be covered in the 382 sequence it is, call it shorter than a semester kind of setting. And therefore, I like to include this here so that you are exposed to actually graphing this stuff out, thinking about it, going through these methods to interpret the data, because that is common in a lot of programs as required course content. And I want you up to speed with your colleagues when you're, say, competing for a job or out working, and you have an opportunity to be doing this stuff, that you'd be in stride with what is expected. And what we have on this is some moisture and density data for a little sample. Consolidation sample would be about the aspect ratio of a hockey puck, and 2.5 inch diameter, a little small for a hockey puck, but ballpark, and 1 inch height. Some parameters are given related to weight volume relationships to let you hammer out what's going on there. Specifically, what you need is an initial void ratio for that specimen. And down here in the lower left, we have the total consolidation settlement for all load increments. And we start with 100 PSF, and we ramp on up to 12,800 PSF, and we measure consolidation all along the way. And then we go through an unloading cycle in which we back off that load and watch the rebound that does occur. And there is some rebound, but it's not elastic by any means, and you'll see that when you sketch this thing out. So this data down here in the lower left is utilized to make this type of graphic. You'll be making a void ratio versus effective stress plotted on a log scale. I just show that as log sigma prime. You're not actually taking the log of the number, but you are plotting those numbers on a log scale. That's typically how it is shown, so that it's easy to work with and you don't have to fiddle around with inverse logs and so on. You just need to interpolate on a log scale. And we should end up with something like this for the loading, and we should end up with a backing off of that unloading. So you would have on the order of 8 points starting at 100 PSF, 200, 400, 800, and I'm not sure where these are going to fall. I'm just guessing here at the moment, but you have several data points to define that bilinear curve. Maybe I'll toss one more in here. It looks like they weren't quite spaced nicely. And then we backed off on this test with an unloading sequence like that. So you're able to graph this from the data that is provided. And what will be involved there for a calculation, back to this, back to the assignment, will be to calculate a void ratio at each of these stress increments. You have a total amount of consolidation present, and you have the starting point, the starting 1 inch height, and a starting void ratio. From this information, you can wring that out. So with that, after loading it with 100 PSF, it's no longer 1 inch. It would be 1 inch minus 0.0029 inches. After 200 PSF, it would be 1 inch minus 0.0045 inches, and so on. And for each of those, you can consider the new phase diagram associated with that of thinking, okay, when it settles, what's going on with volume of solids, what's going on with volume of voids, and you'll come up with a new void ratio for each of these steps to allow you to get a void ratio for each of the stress increments. And that will be the expectation for magnitude of settlement data. You will also be assessing what are the slopes on that curve. That bilinear curve has two slopes associated with it. You will determine those. And you will also determine the preconsolidation stress. And that is available through a Casagrande technique of identifying the knee of the curve using a little bit more refinement than closing one eye and saying there's the knee of the curve. There's actually a graphical procedure to do it, and I can share that with you at a future session. But there will be a little bit of data processing with this such that you would end up with the shallow slope, the steep slope, and the value for the knee of the curve. And again, it's not just eyeballing it. There will be a process for that I'll share with you. Questions on homework 5? I'll do another preview of this, kind of a quick rerun on it after we've seen the time rate of settlement, just to fill in the gaps on what hasn't been discussed here. It relates specifically to this data that you'll be plotting out and making analysis to get at a C sub V parameter using both these methods, a T50 method and a T90 method. And that'll hopefully be crystal clear next week. So straightforward stuff. And I was highlighting some stuff. I did not share screen while I was doing that. That's not very efficient. Let me do that just for a quick sec here. I was showing the time rate stuff is here in the upper left portion, and you will be determining C sub V using these two techniques. And again, we will cover that next week. So stay tuned on that coverage. Questions on that guy? Homework 5. Fairly involved, but I think you'll find once you're in there, it plods along in a fairly straightforward manner and really gets you into the process numerous times in the case of that fiber optic thing. And that's the intent, that you're really driving home the methodology that way of, okay, here's how I do this, and so on. All right, just on the stress distribution, just reminder, it is symmetrical, but you need to consider the entire foundation. And that means you're handling the foundation differently in different points, ABC. You'll actually be utilizing the M&N chart differently for those cases because of that symmetry. Let's take a little break here and then regroup and go buzz through the design project and give you a full preview of that. And we're at 3:06, so maybe we can